Good day, I'm Norman Wildberger. We're moving towards establishing calculus in a very elementary way, using only high school algebra that's at the year 9 or year 10 level. Today we're going to talk about tangent lines and tangent conics to polynumbers or polynomials. We haven't yet introduced the connection between polynomials and polynumbers and geometry, so there are no pictures as yet to connect with these notions. I'm doing that on purpose because I want to emphasize to you that what we're doing here is completely 100% algebraic. In our next video we are going to talk about pictures, and we're going to introduce diagrams that illustrate some of the computations we're going to make today. So let me remind you about the notion of the degree of a polynomial or a polynumber. Here's a polynumber p in our standard form. a0 plus a1 alpha all the way up to an alpha to the n. And if this top coefficient here is non-zero, then we'll say that the degree of p is n. There's one slightly ambiguous case when you have a polynumber which is the zero polynumber. In other words, there are no alpha terms, it's just 0 where a0 is. In that case, strictly speaking, that object there is not non-zero. So it's not clear what the degree should be. So we say that the degree of 0 is undefined. However, if you have a constant polynomial such as p equals 5, then its degree would be 0 because the first non-zero term occurs in order 0. Now we're going to introduce some notation that distinguishes the relative complexity of polynomials of different degrees. A degree 1 polynomial will be called linear. We'll say that a polynomial or a polynumber is quadratic precisely when its degree is 2. Degree 3 is cubic, degree 4 quartic, degree 5 quintic, and we could keep going. And a little bit of a special case, actually the 0th case, when the degree of p is 0, then we'll say that p is a constant polynomial or a constant polynumber. And we'll also include the case when p is equal to the 0 polynomial itself. That's also a constant polynomial, even though, as we've remarked, its degree is not officially anything at all. So we have this idea now that polynumbers come in sort of levels of complexity. The higher the degree, generally speaking, the more complicated the polynumber is. The more subtle its arithmetic is, the more complicated the associated geometry is going to turn out to be. So this is a kind of a hierarchy that the higher the degree is, the more complicated things get. A consequence of that way of thinking is that if we have a high degree polynumber, then to some purposes we might be able to simplify it by casting away some of the higher order terms. We would then get some simpler polynumbers associated to the bigger one. This is a very interesting and useful idea. The idea that we might be able to get simpler polynomials from a given polynomial by truncating it. By truncate we mean we just take some initial part of the polynumber. So the official definition, if p is this polynumber here, the same one as we've been talking about, then for any k, 0, 1, 2, up to n, the kth tangent of p at 0 is this new polynumber that you get by just going up to the degree k terms and no further. It's a truncation of the original polynumber, and we're giving it something of a fancy name. We're calling it a tangent of p. And for a reason which is not perhaps too clear as yet, but will become clearer later, we're saying that this is a tangent of p at 0. Now we can do this at level 0, so that would be the 0th tangent if we just chopped off everything and just left a 0. If we chopped off everything beyond here, just that would be the linear part, that would be the first tangent. This would be the second tangent. And we can keep going all the way up to, well, the whole thing, which would be the nth tangent. That would be all of P itself. We wouldn't have lost anything in that case. So here's a particular example. If P is 8 minus 5 alpha plus 4 alpha cubed minus alpha to the 4th, then the 0th tangent of P at 0 is 8. We just take the terms of degree 0. The first tangent of P at 0 is 8 minus 5 alpha. The second tangent of P is also 8 minus 5 alpha because there are no alpha squared terms here. Or we could say it another way, we could say the alpha squared term here has coefficient 0. So if we include that, we're not getting anything more than we got at this stage. So it's possible for these two tangents of P to be the same. And the third tangent is what we get when we go all the way up to degree 3. It's 8 minus 5 alpha plus 4 alpha cubed. And I didn't write down the fourth tangent. The fourth tangent would be all of P. So the polynomial P has these different tangents at 0. So it turns out that we can define tangents at other points or values too, not just 0. That's going to be a very useful thing for us to do. So how are we going to do that? We're going to do that by rewriting the Taylor by Pauli number. Let's stick with this example here that's quite familiar to us. P equals 8 minus 5 alpha plus 4 alpha cubed minus alpha to the 4th. Here is the Taylor by Pauli number, which we've seen several times. And just what you get when you replace alpha with alpha plus beta. That's all. And then we can evaluate that by essentially expanding out these powers of alpha plus beta. And the easiest way to do that is to use the Pascal's array, and just to multiply the diagonals of the Pascal's array by the various coefficients here. If we do that and then organize things so that we have powers of beta increasing, then we get this expression here, which we've seen before. There's the original Pauli number. There's its first subderivative, second subderivative, third subderivative, fourth subderivative. Now what we haven't done before, and what we're going to do now, is introduce a little bit of a twist. The Taylor by Pauli number is symmetrical in alpha and beta. So we can write it not just this way, but we can write it in exactly the same form with the alphas and betas interchanged. That should be just as reasonable a thing to do, because the thing is symmetric in alpha and beta. So from here to here, nothing but just interchanging alphas and betas. But the interpretation is quite different. What we're going to do now is think of this as being a Pauli number in which the beta can be replaced with a number c, a particular integer c. We're working here with integral Pauli numbers for now, and so when we talk about numbers here, typically they'll always be integers. Although the same discussion will also work with other kinds of Pauli numbers, as we'll see later on. Okay, so for example, suppose that beta, we agree, is going to be replaced with 1. Then this whole expression here is P of alpha plus 1 on this side equals, well, what does this become if beta is equal to 1? Well, here we would have to evaluate this. We would have to 8 minus 5 plus 4 minus 1, that's 6. And minus 5 plus 12 minus 4 is 3. And 12 minus 6 is 6. 4 minus 4 is 0, so there's no alpha cubed term, and minus 1 alpha to the 4th. So this is just an identity. This is a true fact that if you take this Pauli number and you evaluate it at alpha plus 1, in other words, replace alpha with alpha plus 1, and expand out, you're going to get this new looking object. So this is a translate of P by 1. This is not P itself, this is the translate of P to the left by 1. We're going to do something rather interesting now to this formula that we've just obtained. So here it is again, P alpha plus 1 equals 6 plus 3 alpha plus 6 alpha squared minus alpha to the 4th. What we're going to do is we're going to replace alpha here with alpha minus 1, with the idea of recovering P of alpha on the left-hand side. So P of alpha is just the original Pauli number that we started with. When we replace alpha with alpha minus 1 here, we also have to replace it with alpha minus 1 here, and here, and here. So we get a new formula that says that the original Pauli number P is written as 6 plus 3 alpha minus 1 plus 6 alpha minus 1 squared minus alpha minus 1 to the 4th. Have a very good look at this. What have we done? We have rewritten the Pauli number so that it is not expressed as a sum of powers of alpha, but rather as a sum of powers of alpha minus 1. Something plus something times alpha minus 1 plus something times alpha minus 1 squared plus something times alpha minus 1 cubed plus something times alpha minus 1 to the 4th. Now I think it's a good exercise for you to check this, to make sure that this is actually a true statement. That if you expand this all out, just using the standard laws for manipulation of polynomials or polynumbers, that you will recover the original Pauli number P. Okay, so that might be a good exercise to do. So we're going to use this formula to define the kth tangent to P at 1. So how are we going to do that? And I've just reminded you what the original Pauli number P was there, all right? So we're going to take this expression here and we're going to view it in the same way as what we did when we were truncating the original Pauli number. The 0th tangent is what we get when we just take the degree 0 term here, which is 6. The first tangent is what we get when we just take the linear part, or the part of degree up to 1. 6 plus 3 alpha minus 1. Now we can expand that out and rewrite it as 3 plus 3 alpha. The second tangent to P at 1 is what we get when we take this and we go up to degree 2 terms. So we truncate everything past here. We have 6 plus 3 alpha minus 1 plus 6 alpha minus 1 squared. And here I've expanded that out and collected terms. So it simplifies to 9 minus 9 alpha plus 6 alpha squared. The third one, when we go up to degree 3, well, it's going to be the same as the one of degree 2 because there are no cubic powers of alpha minus 1 there. We get 4 tangents to P at 1. We're going to give these some names or interpret them. First of all, the 0th one is just the value of P at 1. If you plug 1 into here, you're going to get 6. So the significance of this is the value of P at the point 1 that we're considering. This first tangent, we're going to give it an alternate name. We're going to call it the tangent line of P at 1. And the second one, well, we're going to call that the tangent conic of P at 1. This third one, well, to follow the pattern, we would call it the tangent cubic of P at 1, but in fact it's not actually a cubic at all because it doesn't have any degree 3 terms, so we'll be a little bit ambiguous. We won't call that anything yet. But this will be the tangent line of P at 1. This is the tangent conic of P at 1. These are absolutely fundamental constructions in the differential calculus. The differential calculus is all about these kinds of approximations to polynumbers and other more general objects. But if you understand the story for polynumbers or polynomials, then the higher order stuff falls naturally into place. In fact, it's in some sense not such an extension. The heart of the algebraic aspect is contained here in the polynumber case. So if you have taken a course in calculus before, you will of course have studied tangent lines to curves or to functions. You probably will not have studied tangent conics very much. That might be kind of a new idea for you. It's actually a very interesting idea. It's an underrated idea, let's put it that way. And we're going to see the importance of tangent conics a little bit later. But if you haven't studied calculus before, you might say, well, okay, we can do this, we can play this game, but what's the point? What do we gain? Okay, well, here's a very natural and a good answer to what we can gain by studying tangents to polynumbers. The point is that we can approximate evaluations of polynumbers. Let's illustrate again by sticking with our standard example of p like there. And I'm just reminding you that at c equals 0, the various tangents were these. That was the 0th tangent, that was the first tangent, that was also the second tangent, and the third tangent was that. Suppose we want to evaluate p of 0.03, a purely arithmetical issue. We want to plug 0.03 into this expression here, and we want to compute it. Suppose we don't have a calculator. We have to do this by hand. Well, I'll tell you what the answer is. Okay, here's the actual answer right here. 7.85010719. You plug this thing into here, and that's what you get. But you might not be interested in knowing this to 8 decimal places. You might just be interested in knowing it to the closest integer, or to 1 or 2 decimal places. This might represent a level of magnification that's uninteresting to you. Well, that happens in practice quite a lot. And the tangents of the polynumber help us in evaluating. So let's see how. Let's take the 0th tangent, the simplest one, which is just what we get when we throw everything away except for the constant term. That's 8. If we take that thing, which is a polynumber, and we evaluate it at 0.03, well, we just get 8. So that's a kind of a naive initial approximation to what p of this thing is, because this number is pretty close to 0. The idea is that this number is pretty close to 0, so alpha is pretty small, alpha cubed is even smaller, alpha to the 4th is even smaller. So these things here will be relatively small, and the main term here that will contribute to the sum will be the 8. That's very good thinking. Okay, we can go one step further. We can go to the first tangent, which is 8 minus 5 alpha. So we'll take that polynumber and plug in alpha equals 0.03. So we take 8 minus 5 times 0.03. We evaluate that with our pencil and paper. We get 7.85. That's a little bit of a better answer than the first one, because we've taken more terms of the whole thing. Our error is smaller. The error that we're dropping are these 2 terms. One step further to the third, actually I guess it's 2 steps, because one step further would be the second tangent, which is the same as the first tangent. But if we go to the third tangent, which is 8 minus 5 alpha plus 4 alpha cubed, and evaluate it at 0.03, do the calculation, we get 7.850108. That's yet a closer approximation. Now we've only dropped 1 term. We've just disregarded the alpha to the 4th. And the actual value, when we calculate the whole thing, including the 0.03 to the fourth, is this number here. So you can see that because the 0.03 happened to be close to 0, plugging it into the various tangents gave us approximations to the actual value. And for many purposes, those approximations would be good enough and would relieve us of the need to make a computation that was more complicated than it had to be. So that was fun. Let's do another example. We'll stick with the same polynumber p, but now we're going to try to approximate p of 1.07. This number is pretty close to 1, and it's not so close to 0 now. So if we just plug this into here, and we ignore, say, the last two terms, then we'll have a reasonably big error. We will not have a very good approximation. And that's because, in some sense, this polynumber, the way it's written now, is geared to the point 0, because it's powers of alpha, which get small as alpha approaches 0. This value is close to 1. And so what we're going to be looking at is rewriting the polynumber in such a way that it's now in powers of alpha minus 1. We've already done that. Okay? That was what we did when we calculated the various tangents to p at 1. So we took this thing here and we took various truncations of it to get the 0th tangent at 1, the first tangent at 1, the second tangent at 1, which is also the third tangent. So let's use these things as approximations to the true value of p, which is all of this. Let's plug in 1.07. First, into the 0th tangent. We plug that in, it doesn't matter what it is, we're going to get 6. That's an approximate value to p of 1.07. A better approximation with the first tangent, which is 3 plus 3 alpha. We plug in 1.07, we get 6.21. That's now a better approximation. Has 2 decimal places. The second tangent, which happens to also be the same as the third tangent, is 9 minus 9 alpha plus 6 alpha squared. When we plug 1.07 into that, we have to make this calculation. Okay, we can do that. We get 6.2394. We have now 4 decimal places. We have more accuracy than we did here. And we see that we're still in the same general ballpark, but it's getting more accurate. And of course, we should compare it to the actual value. If you actually take the whole Pauli number and you plug in 1.07, so going right back to the start, and evaluate it, you get 6.23937599. That's the exact answer. This is a pretty good approximation. That's not quite so good. That's not quite so good. But all of them are pretty decent. And why does it work? It works because, first of all, 1.07 is pretty close to 1. And secondly, because we're essentially using this representation of p. The fact that we've essentially rewritten it as something involving powers of alpha minus 1 rather than powers of alpha. And why is that good? That's good because if this number is pretty close to 1, then the difference between alpha and 1 is small, like close to 0. And so when we square it, or we take its 4th power, we're going to getting something that's small. So that means this representation is ideal when we're evaluating the Pauli number at a value which is close to 1. This representation is good when we're evaluating for an alpha close to 0. And I think you can see the idea. If we were evaluating at some number that was close to 7, Then we would want to look for another representation of the same polynumber in powers essentially of alpha minus 7. So we've looked at this polynumber with the special constants 0 and 1, but we could just as well have looked at other constants, c equals 7 or c equals minus 5. So we want to get a sense of, well, how does this actually work somewhat more generally? So often things are clarified when we look at them not in very special cases, but somewhat in more generality. So let's look at what we've been doing from a little bit more of a bird's eye view. What's really going on? Well, we've started with a polynumber p. And let's assume we have a general polynumber. A0 plus A1 alpha all the way up to AN alpha to the n. The basic object, in some sense, that starts this entire discussion is the Taylor bipolynumber. What we get when we replace alpha with alpha plus beta. When we do that and write it out in terms of powers of beta, then the various coefficients are going to be themselves polynomials in alpha, or polynumbers in alpha. And the various polynumbers that we're getting here are the subderivatives of p. The zeroth subderivative of p, which is p itself. The first subderivative of p, which is the same as the derivative of p. Then the second subderivative, the third subderivative, all the way up to the nth subderivative. Okay, so now what we're doing in today's lecture is we're turning this around. We're taking this equation and replacing the alphas and the betas. So instead of having powers of beta increasing here, we now have powers of alpha increasing. And now these coefficients, instead of being polynumbers in alpha, they are now polynumbers in beta. So I'll make that explicit by writing d0p of beta, d1 of p of beta, all the way up to dn of p of beta. So these are the various subderivatives evaluated at beta instead of alpha, because we're interchanging the alphas and the betas. So that's just the Taylor bipolynumber sort of rewritten. Okay, so what did we do then in our examples? Well, we let beta be now a constant number. Instead of being a polynumber, we're replacing it or evaluating it at a number c. C is for us an integer, since we're working here all over the integers. So we're just going to rewrite this formula with beta replaced with c. P of alpha plus c equals d0 of p of c plus d1 of p of c times alpha plus, and I put in the next term, d sub 2 of p of c times alpha squared, all the way up to d sub n of p of c times alpha to the n. That's quite a nice formula, right? You should stare at that formula. But we're going to modify it a little bit to make it a little bit more familiar. We're going to replace alpha now with alpha minus c. So we're going to translate this formula. So if we replace alpha here with alpha minus c, then on the left-hand side we'll just have p of alpha, which is, of course, the original polynumber we started with, namely that thing there. What happens to the right-hand side? Well, we just have to go through and replace all the alphas with alpha minus c. So we get d0 of p of c plus d1 of p of c times alpha minus c plus d2 of p of c times alpha minus c squared plus all the way up to dn of p of c evaluated at alpha minus c to the n. We're going to give this a name. This is a very important expression in calculus. It's something that first-year students agonize over. Many of them never learn it properly. Partly it's because they're not told the right way of thinking about it. And in fact, they're not even given the right sort of formulation. This is a superior formulation to the one that you find in calculus texts, because it involves the subderivatives rather than the powers of the derivative. It's the Taylor expansion of P at C. But because we've written it with subderivatives, there are no factorials floating around in the denominators. So we don't have to do rational arithmetic, we're doing integer arithmetic. So if you have taken calculus before, flag that point, okay? It's really the same formula as the Taylor expansion that you're used to, but it's written differently because these are subderivatives rather than powers of the derivative. As a result, there's no 1 factorial, 2 factorial, n factorial in the denominators here. This is all over the integers. Okay, so this is a great formula. It's a very general formula. It includes the various formulas that we've already looked at in special cases. So we've had a look at the special case when P was that polynomial 8 minus 5 alpha plus whatever it was, 4 alpha cubed minus alpha to the fourth, whatever. We looked at that case with the special case when C was equal to 0, and also the special case when C was equal to 1. Here's the general case for a general polynomial and for a general constant C. So this has been an important lecture. We've covered a big chunk of vitally crucial material in a first calculus course relating to derivatives, Taylor polynomials, Taylor expansions, use of those things for approximating functions. Don't be afraid to go over it several times, especially perhaps if you have already studied calculus. This may be a little bit unfamiliar way, an unfamiliar approach to the subject. But you should be confident that we're proceeding in a way which is logically completely clear. It's only high school algebra, one step at a time. So I do really want you to get what we've been doing today under your belt. And so I am going to insist strongly, okay, that you do this exercise. Even if it's all clear to you, doing the exercise will solidify it in your mind, because this is a novel way of thinking about things. And so solidification is necessary. What I want you to do is to look at this particular polynumber or polynomial. It's a cubic because it's of degree 3. 5 minus 3 alpha minus 4 alpha squared plus alpha cubed. And I want you to do pretty well all of the things that we've been talking about. First, find the Taylor bipoly of this thing. And I remind you that the easiest way of doing that is to exploit the fact that you know the Pascal array. You're just multiplying diagonals of the Pascal array by these 4 numbers, and then adding up what you've got, organizing what you've got. Find the subderivatives of this polynumber. D0, D1, D2, D3. You can think about what the higher subderivatives will be. Find the k tangents of P at 0. K equals 0, 1, 2, etc. Then find the Taylor expansion of P at a number of different points C. At C equals 1, at C equals 2, at C equals minus 1. So find the k tangents of P at C at these 3 points, at C equals 1, 2, at minus 1. So for each one of these points, you'll have a 0th tangent, a first tangent, a second tangent, a third tangent, so on. And then use those various things to find approximations for, let's say you had to evaluate this thing at 0.02 or 1.05 or 0.97 or 2.03 or 1.94 or minus 1.001. All right, so I want you to go over the lecture, solidify by writing down, nice, neat, in a book, careful, write down solutions to these things. If you do that, and if you're enthusiastic, you can try it for some other polynomials. You can make up your own polynomial. Work things out. Right? It's by working things out that we understand what's going on, and we start saying, actually, this is quite easy. This is so elementary. Why did nobody tell us before that calculus was so easy? Okay, next time we're going to supply a missing aspect to this discussion. We've been doing algebra. We haven't had any pictures. Okay, calculus is not just about algebra. There's many geometrical aspects to it, and so we want to introduce some pictures to go with the algebra. That's going to make us feel even better. So next time we're going to talk about visualizing or graphing polynumbers. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.